Hi everyone, welcome to this exciting physics class where we are going to dive into electromagnetic waves. You might have heard that light is an electromagnetic wave. In fact, all these X-rays, gamma rays, these are all electromagnetic waves, and that's what we are going to look into today. I'm going to make these physics concepts absolutely clear for you. So keep your pen and paper ready and let's begin. Before we get started, just a quick reminder, do check out the courses on our website manochaacademy.com and our Android app Manocha Academy. All the links are given below and please do share it out with your friends as well. So remember, as we talked about in the last class, this great scientist, do you recognize him? He is James Clerk Maxwell, right? And he is the one who had predicted and all his theories on this electromagnetic waves, right? He had predicted the electromagnetic waves. So what did he, what is the key thing that he said? That we knew from Faraday's laws of electromagnetic induction that a changing magnetic field, so a changing magnetic field, it produces an electric field. So Maxwell argued and showed that the reverse also should be true, right? That a changing electric field should induce a magnetic field. And remember this famous experiment where we had the charging of the capacitor, right? So when you turn on the switch, then the charges on these capacitor plates will grow, it will increase, which means that the electric field here, electric field is there between the plates of the capacitor. So this electric field will also increase, and this will induce a magnetic field. It will create a magnetic field around it, and he explained it with the concept of displacement current, which I taught you in the previous class. Okay, so that is why if you see that there will be a displacement, so there is a normal conduction current here, remember we talked about, and there will be a displacement current in this direction. So there will be a displacement current in this direction, ID. So if there is this displacement current, which is actually the change due to the change of electric field, he just called it a displacement current so that we can explain the magnetic field around it. So guys, if you look above it, what will be the direction of the magnetic field? We can just use our right hand thumb rule. This is the direction of the displacement current, and if I curl up my fingers, do you guys agree that this field over here is going to be outwards? So I can draw it with a dot here. And same way, if the current is this way and I curl my fingers, can you see they'll go inwards over here? So the magnetic field here will be inwards. So one thing, if you guys notice carefully here, what is the direction between this electric field E and the magnetic field? Electric field, do you all agree, from the positive to the negative plate, it is in this direction, and magnetic field will be what? Either outward or inwards. So can I say that the electric field and magnetic field are perpendicular to each other? Yes or no? Will you guys agree? So can we write over here that the electric field and magnetic field, they will be perpendicular? And this perpendicular point is very important. It will come again later. Okay. So what did Maxwell predict? Maxwell's great prediction was he showed that the variations in this electric and magnetic field, right? We said that a changing magnetic field induces an electric field, a changing electric field induces a magnetic field, and so this will go on, right? So these variations in electric and magnetic fields, they occur in mutually perpendicular directions, just like I explained to you right now. We just discussed they are perpendicular to each other, okay, in mutually perpendicular directions, and they have wave-like properties. They propagate like a wave. So he theoretically, right, that time he did not do any experiment. The experiment to prove this whole EM theory was done by Hertz, the scientist Hertz, which I think was about 20 years later. But he was a theoretical physicist, right? He predicted the existence of electromagnetic waves, right? And what is your electromagnetic wave? Where basically, what do you have over here? You have this changing electric field, changing magnetic field. So what do I mean by that? Let's discuss this. So basically, what did he predict? That if you take this red axis, the y-axis, as the direction of your electric field, and the z-axis, this one, as the direction of the magnetic field, he predicted that this will continue traveling and your electromagnetic wave will travel here along the x direction. So what he was predicting is that when there is a changing electric field, which we'll talk about, right, not a constant, a changing electric field. So just focus on the red part. This is your changing electric field. That in turn will induce a magnetic field perpendicular to it, right? So this electric field induces the magnetic field, right? Then the magnetic field induces an electric field, then the electric field induces a magnetic field, and so on, right? This process will continue. So these keep getting induced, and you can see they are always perpendicular to each other, and the wave is perpendicular to both these guys. This was Maxwell's prediction, which we'll talk about. So first, let's again go back to the basics of this electric and magnetic field due to a charge. If you consider a charge at rest, like if I just take a charged particle like this, we know that it will have an electric field around it. We have studied Coulomb's law and electric field and all, right? So if you take a positive charge like this, do you guys agree? This is going to have a electric field around it. And we represent by these electric field lines which are going away from the charge, yes or no? So this is the electric field around it. This is a charge at rest. So charge at rest creates an electric field. A charge in uniform motion, right? So suppose I take this charge and I give it a constant velocity, right? So it is moving in uniform motion, let's say at a constant velocity v. Okay? Then the scientist said that this charge, when it is in uniform motion, that means what is it? A charge in motion, what do you guys call it? It's a current. And we know that a charge in motion is a current. Current produces a magnetic field around it, right? So there is going to be a magnetic field, which we can again, decide by the right hand thumb rule. So we can clearly see that a charge in motion will produce a magnetic field around it, which I denote by the symbol B. Do you guys agree? Now you'll say that what about the, will it have an electric field around it also? Yes, right? But one main important difference here is there is no magnetic field because it's at rest. Here, because of current, there is definitely a magnetic field. Okay. Now this charge will also have an electric field around it, but because charge is in uniform motion and this gets into some relativity theory and also we don't consider that, we consider it as out of scope and we are focusing only on the magnetic field. Okay. But the third case is the most interesting, that when a charge is in acceleration, then it produces both your electric and magnetic fields. So a charge in acceleration, that will create both E and B. So this is when a charge is moving in acceleration, right? When a charge is in under acceleration. Okay, not in uniform motion. Then there will be both an electric and magnetic field, and so you can guess that who will produce the electromagnetic wave, this option, or this option. So if I tell you which case will give me electromagnetic waves, come on, tell me in the comments. That's right, the third case, right? Because here there's only electric field, here there's only magnetic field, where yes, there is some relativity here, we are ignoring the electric field. So this is the main one, right, which we'll be talking about. Now the easiest way to get a charge in acceleration is to oscillate the charge, right? Rather than just making it move in some random direction and then running after it, you just oscillate the charge. Okay, so why oscillation? Think about it. So if this is the center position, mean position, and if I make the charge move like this in this kind of oscillatory motion, then back, then again here, and then back to the mean position. So if I give it this kind of oscillatory motion like a pendulum, do you guys agree? We have studied in simple harmonic motion also, that is a case of acceleration, right? Because when it is, so here it is having the maximum speed, here the velocity is going to be 0 and then it changes back, and here also the velocity is going to be 0. Okay, so the charge is clearly under acceleration, right? Clearly under acceleration. So oscillating charge is very important. It is a charge in acceleration, and charge in acceleration means, what does it mean? It will produce both electric and magnetic fields. So we are confident here that we will get electric and magnetic fields will be produced. Yes or no? And this is what the scientists have observed also, right? So this is an accelerating charge, and the best case is the oscillating charge. Now, have we studied charges in oscillation before? Have we studied it? Tell me. Have you heard of this oscillation before? And the answer is yes. LC oscillator circuit, right? We had done this class on, if you have missed it, please watch my video on LC oscillations. What is LC oscillations? L is your inductor, C is your capacitor. C is the capacitor here, this is my inductor. And remember what is happening over here? When you start off with the charged capacitor having plus Q and minus Q, remember charge was flowing from it and the charge there was decreasing. So the charges will decrease. Yes or no? Charges will decrease, and then finally the charge will become zero over here. Capacitor will get zero charge, and then inductor runs the show. Remember, inductor would run the current, right? So inductor will be running the current and then charge the capacitor in the opposite direction, plus Q and minus Q. And then once again the charge will, so here it will get charged, so charge will increase, and then again the same thing will continue. Then again it will get discharged and decrease it. So these oscillations will continue. So basically, can you see that since it is oscillating like this, do you guys agree that here the charges are in acceleration, right? It is a case of charges in acceleration because it is this kind of oscillatory behavior. It is not a constant. It is not a constant motion. It is getting discharged here, then again coming to zero, then again getting charged up, right? And it is remember this inductor is creating the back EMF. So if you have missed this class, please watch the LC oscillation. But for now, you have to trust me that LC oscillation, basically your charges are oscillating. Charges are in oscillation. Charge means the charge on the capacitor, right? So charges are in oscillation. Now if charges are in oscillation, that means charges are in acceleration. And if charges are in acceleration, it will produce electric and magnetic field. So we can say that the LC oscillator circuit is a great source of electromagnetic waves, right? So we can say as a result, do you guys agree? So as a result, this will produce electromagnetic waves. And in fact, Hertz used this, right? The scientist Hertz used this to prove it, right? So Hertz, in fact, used Hertz's famous experiment. He used it, the LC oscillator circuit, to show that this can produce electromagnetic waves. So when this charge is oscillating, right? When the charges are oscillating, so do you guys agree that here the electric field will be the strongest? The electric field here will be maximum. Then here the electric field is weakest, minimum or zero. Then here the electric field is maximum, but now in the opposite direction. So can you see that there is an oscillation in the electric field? Yes or no? There is an oscillation in the electric field. So definitely we are getting a oscillating electric field. The capacitor is getting an oscillating electric field. Do you guys agree? Yes or no? And this oscillating electric field will also produce a oscillating magnetic field, right? Which is associated with the inductor over here. Clear? So clearly there is an oscillating electric field, and this will produce your oscillating magnetic field. So get your concepts clear, absolutely clear. And this will produce your electromagnetic waves. Okay. Now if I ask you one interesting question, electromagnetic waves, like this light, infrared, radio waves, all of these are electromagnetic waves, right? And you can watch my video. I have a video on electromagnetic spectrum. So these waves are different because they are different frequency. So can you tell me what will be the frequency of the electromagnetic wave emitted by the the LC circuit? Remember, we have a formula for that LC resonance. Do you guys remember? When these oscillations will continue. So exactly you can use that formula, that omega equal to 1 by root LC. That will give you the frequency, or frequency if you want it in F. This is angular frequency, 1 by 2 pi root LC, and this will be the frequency of your electromagnetic wave. Okay, so you can tune it to the frequency that you want for the electromagnetic wave. Okay, very, very important connection here. Frequency of oscillation of the circuit is equal to the frequency of the electromagnetic wave produced. Okay, so as we discussed, electromagnetic waves, these are the special waves like light waves, right? Light is the best simple example you can remember, and they are radiated by a accelerated charge. They are radiated by an accelerated charge, or we were saying oscillating charge, right? And it propagates through space. Light travels through space, coupled as electric and magnetic fields which are oscillating perpendicular to each other. So if you look here at this diagram, can you see, if you take the red one as the red one is suppose our electric field, okay, along the y-axis. So you can see this is the y-axis and this is my electric field along the y-axis. This is the z-axis. It doesn't have to be, right? In this diagram it is. This is the magnetic field, and my wave propagation is happening along which direction? The white line, the x-axis is my electromagnetic wave. So the wave goes this way. So basically what is happening over here, look that when you are having this changing electric field, how is it changing electric field? I just explained you with the LC oscillator circuit. Can you see that there is a varying electric field from maximum to 0 to minimum, right? On the maximum negative value, then again it will oscillate. So there will be a continuously varying electric field. Okay, varying electric field, let's say in a particular direction. Here we are considering in the y direction. So electric field is varying, oscillating in this y direction, vertical direction. Okay, this will produce a magnetic field perpendicular to it, let's say in the z direction here. Okay, so everybody look at me carefully. So let's say I use this marker and the pen here. Okay, so let's say guys, this is my electric field in the vertical direction. Okay, this will produce a magnetic field in the perpendicular direction, this white marker, right, this white pen here, in the perpendicular direction. And so can you see the red one is the electric field oscillating, this is the magnetic field, and the wave will propagate along the x. So it's going to happen like this. Take a look now. So here's your moving electric field, moving magnetic field, and the wave is propagating. Can you see that? This is what's going to happen. See, moving electric field, moving magnetic field, and I am the wave. Got it? So that's exactly what is happening. And the wave direction, can you see here? The wave direction is perpendicular to these oscillating fields. Clear? So this visualization should be very clear to you. Now you guys know this transverse and longitudinal waves. Remember, in transverse wave, like if you take this, like you take a string or this slinky over here, and basically what is happening here in a transverse wave, the wave travels this way. The wave is traveling this way, but the particle oscillation, here we are taking the mechanical waves where there are particles. In electromagnetic waves, we'll talk about there are no particles, right? So here basically the movement of the particles, if you consider any particle, can you see that the vibration or the movement of the particles is perpendicular to the wave, direction of the wave? So this type of wave is called a transverse wave. And this type of wave where the particle vibration or the movement and the wave direction are along the same line, this type is called a longitudinal wave. So now you tell me, electromagnetic wave, one important difference is electromagnetic wave, it propagates through space. So it doesn't need a medium, but at least we can classify based on transverse and longitudinal, which category does it belong to? You tell me. Will you choose for electromagnetic wave, will you choose transverse or longitudinal? So the important difference I told you here, there is no particle, right? It is the electric and magnetic fields, the variation in fields, and that is why electromagnetic wave can travel through vacuum, through space. You don't need a medium. Sound needs a medium, okay? But clearly you can see that here the vibrations or the variations of both, the electric field is perpendicular, can you see? the vibration of the electric field is perpendicular to the wave. Same way magnetic field is perpendicular to the wave propagation. So definitely electromagnetic wave is a transverse wave. Will you guys agree? Okay. And one important thing here we'll say, electromagnetic wave does not need medium for propagation. It does not need particles because it is purely movement of these electric and magnetic fields which don't need any particle, right? Field doesn't need particle. So this is very important that it is a transverse nature. As we discussed, it is transverse because the electric field is perpendicular. Check here, check. If you don't believe me, you check. The electric field here, E, is along this direction, right? E is along the Y direction. Z, so this was the Y direction, let's label it. E is along the Y. Magnetic field is along the Z. And the wave is along the X direction. So will you guys agree with me if I say electric field is perpendicular to the direction of propagation? Magnetic field is also perpendicular. Check it, 90 degree, right? And the direction of the propagation here is along the X. But here you will have one doubt. You will say, sir, does it go in the positive X or the negative X? That's an interesting question, right? Because if I made the arrow this way also, then also they are perpendicular. So how do I know, sir, it is going this way? Why not going that way? So there is a rule here that the direction, what is the direction of propagation? Do you guys know? So what is the direction of the propagation? Direction of the propagation is actually E cross B. So you cannot take any random direction. It is the vector product of E and B, the cross product of E cross B. Okay. So here if you check the cross product of E cross B, what will it get? So when you are going from E to B, can you see? We are pointing in this direction, right? So you have to take a cross product from E to B. Okay. Cross product from E to B, it points in this direction. Clear? So in fact you can take it like this. Your Y is along the, so basically our electric field is J along the Y axis, so J cap. Magnetic field is along the Z axis, so K cap. And J cross K, you know, is nothing but I cap. Remember that we have discussed in cross products I, J, K. So when you are going from J to K, you go to I, that whole circular rule. So clearly you are getting I cap over here, which is the direction along the X axis. Is that clear? So direction of propagation is E cross B, and yes, it is sort of like a double transverse wave, right? Because the electric field is also perpendicular to the wave direction and the magnetic field. Now we are going to look at the equation. We are going to discuss the equation of the electromagnetic wave, right? Which is basically the equation of the electric and magnetic fields. But before that, let's quickly revise some important terms which you might have forgotten, which are very important for the wave equations. Okay, so we'll just do a quick recap on that. So starting with amplitude. Amplitude, all of you remember, it is the maximum displacement from mean position. So clearly here, what is the amplitude? This is the maximum. So this is my amplitude, right? Maximum displacement from mean position, and here it is of the electric and magnetic fields because no particle is displacing, right? It is of the electric and magnetic field. So that is amplitude. Time period is what? Time taken for one complete oscillation, right? One complete oscillation of the electric field and the magnetic field. Now one thing here interesting is that both take the same time, right? So you can see that the time taken for the electric field is the same time taken for the magnetic field, and we'll see they are in phase, they are in sync. They're like dancing in sync with each other. So when this guy is going up, this guy is going up. When this guy is coming down, this guy is coming this way, right? So they are all, you can see, it's all happening. They're dancing together. Okay. So time period is the time for oscillation of the electric field or the magnetic field for our EM wave, right? These are of course the general terms. Frequency, remember, number of waves produced per unit time, and the unit is hertz. This one, the unit is seconds. Amplitude, you know, meter is the SI unit. Now angular frequency. What is angular frequency? Angular frequency, remember, rate of change of phase with time, or that omega we can define like this, measured in radians per second. So 2 pi f, remember its connection, your angular frequency. Wavelength, distance covered by the wave during one time period, simple. Wave number, number of waves present in the unit distance. So all these basic terms we have studied earlier in the wave chapter. Now there's one more important term over here, the angular wave number, which remember we used to call it as k, is 2 pi by lambda. It's also known as the propagation constant, very important. This k is 2 pi by lambda and we'll be using it in the equations. And then your wave velocity, your phase velocity is the distance covered by the wave in per unit time. And here you guys remember the connection between V, F and lambda. So all of you remember, like we have studied in sound, here also V is equal to F lambda. Velocity, wave velocity is frequency times the wavelength. So now let's come to the equations. Before we come to the electromagnetic, see I'm going step by step. Before we come to the electromagnetic wave equation, let's quickly discuss the harmonic equations we have studied in the for harmonic waves, right? So remember it was of this form, A sine, A is your amplitude, sine omega t, omega is your angular frequency, plus minus k, k is that propagation constant I just showed you right now, 2 pi by lambda, that is the k, okay, times x plus whatever your initial phase. So these all are your equations that we have done. And the velocity of the wave, there is a nice formula. So one is that F lambda and it is also equal to omega by k. You can check it here because remember omega is 2 pi f, k is 2 pi by lambda. So if you take it up, you will see you will get F lambda. Now this is the basic velocity formula, omega your angular frequency by the propagation constant, k, right? This k, your wave number, angular wave number or propagation constant. So remember we used to look at these kind of equations, A sine omega t plus minus kx plus phi naught, or you might see it as kx plus minus omega t, doesn't matter, okay. So this is your equation. Now the omega we can write it as 2 pi f or 2 pi divided by time period. So omega can be written like this, see k can be written like this, 2 pi by lambda x plus phi naught is your initial phase. Now these could be sine functions or cos functions, doesn't matter, they are all periodic. So they are so remember this electromagnetic will be following this beautiful sine or cosine, right, the wave pattern, the trigonometric functions. Is that clear? And do you guys remember that why have I put this plus minus? So suppose if you have, so if you take this equation, do you guys remember this point? If you take y is A sine omega t minus kx, and I'll ignore the phase for now, or if we take A sine omega t plus kx. What is the difference between these two waves? Whenever you have a minus, a minus like this means that the wave is traveling along the positive x-axis, and we know x-axis because there's an x term over there, right? Because this is the, what is the y? This y is the amplitude, the amplitude in variation with the time and the distance from where you're measuring it, right? So I'll talk about that t and x. So, or let's talk about that first and then we'll come to this. So you guys remember, so when we are talking about this wave equation, if you go back and revise your wave chapter, so it is this equation, right? And what are we trying to predict? What are we trying to predict, guys? We are trying to predict at a certain moment in time, so at a certain time t, and let's say at a certain distance x here, what is the amplitude? How much is the amplitude of vibration? So this is my y. See, because the amplitude of the particle, right, here we are talking about particle, there it will be electric field and magnetic field. The amplitude or the displacement of the particle depends on the time that you are taking the photograph and which particle, right, the distance from your origin over here. So that is why y is a function of both x and t, the position of the particle x and the time at which you took the snapshot. And when you plug in these values, you will get its displacement. Got it? Got it? So that is the meaning of this wave equation. It beautifully captures everything. It captures the time parameter, the position parameter, and if there's any initial phase, right? So the starting point, the measurement point, right? So when you have this difference a sine omega t minus kx and a sine omega t plus kx, what is the difference here? Minus kx tells you that the wave is propagating in the positive x direction. So whenever you have this, that means wave along. So I can put the heading here, wave direction. So this will be positive x-axis. So when you have a minus sign, that means wave is along positive x-axis. When you have a positive sign, it's in the opposite direction, negative x-axis. Okay? And this is x because the variable is x. So why I reminded you all of that? Because see, we are going to use it here. Our electric field, remember what Maxwell said, it's a time varying electric field. So it is varying with time and with the position, right? Position from your starting point. So can you see in the wave? It is varying with time and your starting position, right? Where are you? Where are you measuring it from? So the whole amplitude means this, right? It depends on the time that you're taken and at which point you're doing the measurement. So your electric field will look like this, E naught means the amplitude maximum, sine omega t minus kx. So here I have assumed that the wave is propagating along the positive x direction. So you can see here, that's why I have taken minus kx. If it is going this way, I would have taken plus kx. Make sense? So my wave is going this way. So E naught, maximum electric field, sine omega t minus kx. Do all of you agree with this equation? Do you understand this equation? And why have I written a x comma t? Because the amplitude of the electric field depends on the time you are measuring and the distance from the origin. Okay? And don't forget again, this omega and k are connected like this with the wave velocity, very useful formula. This is your velocity of your electromagnetic waves. Okay? So V equal to omega by k. So right now guys, we are focused on the equation of the electric field which is along the y-axis. So we are focused on the equation of the electric field. So this answer will give you the y position. So basically what are we measuring? You are measuring, you can say your Ey over here, which is basically a function of x and t. Clear? Now as we discussed, omega we can replace, omega is our angular frequency, we can replace it as 2 pi by the time period. K, our propagation constant, we can replace as 2 pi by lambda, right? So just learn this formula one by one. So nothing, if you know omega, what is this? You just have to do a simple replacement. Then again you can take 2 pi common here and it becomes nice and beautiful like this. Clear? So this is once again the equation. This is the equation of what? The electric field. The electric field. You'll say, what about the magnetic field? Don't worry, it's coming up, right? So this is not the complete equation of the electromagnetic wave. You can say this is the equation of my electric field. But it's giving me information. It's giving me information like the maximum amplitude, the time period, the wavelength, all this stuff is captured here. And the fact, one more information, important information, that since there is a x variable, that means it's traveling along the x-axis. If there's a y variable here, maybe the wave is going in this way. The electric field is perpendicular to it, right? So the variable is very important. X because it is propagation wave along x-axis. So that's the important information we have got from the equation. Besides all the time period or whatever frequency and the omega and the k. Next we'll look at the magnetic field equation, right? So we talked about the electric field equation. Now we'll look at our magnetic field which is along the z-axis. It can be anywhere, but it should be perpendicular to electric field. Okay. So magnetic field symbol B, right? X comma t. X means as a function of the distance from this position, right? Because my wave is traveling along the x. Correct? So same thing. This will become B naught sine omega t minus kx. Now you will say, but sir, why don't you write omega 1, k1, omega 2, k2? This is a very beautiful thing about the electromagnetic wave. They are in phase. Both electric and magnetic fields have the same angular frequency, same k. Okay. So note this one very important point. Both E and B, same omega, same k. Basically they are in phase. And if there is any phase angle also plus phi naught, that will be the same. Okay. So these guys are totally dancing together and they are totally friends with each other. They are in phase. which makes it life easy for us, right? And now you can see the omega will be this thing, 2 pi by t, same thing, I've just repeated it, same thing, take it in common. Nothing great here, okay? So this is the equation of the magnetic field. Clear? So what is really the equation of the electromagnetic wave? Actually both of these, right? So electromagnetic waves is this and this. One important thing that the B is now along the Z axis. So really we are looking at, so sometimes you'll see it's written like this. Really we are measuring the BZ over here, and here we are measuring the EY. Magnetic electric field is in red color, so I'll put it in red. So see, we have given all the things, right? Or sometimes it will say this is, they'll put a, it's along the Y axis, so they'll put a IJ, a J cap over here. They can give you a direction, so simple, right? They can specify the direction in the equation itself, or write it as a subscript. Clear? So again, doesn't have to be that the electric field has to be only along the Y, it can be along the Z, then magnetic field can be along something else, right? And it must follow that E cross B. The direction of wave propagation should be electric field cross the magnetic field. Clear? Now what is the relation between the amplitudes? Amplitude means the maximum value, right? So what is my E naught over here? What is my B naught over here? The maximum. Can you see that? And this is a very important formula, the relation between these guys, E naught by B naught, this ratio is equal to C. Do you guys know what is C, small c? E equal to mc square. That's right, that same C, the speed of light. So please write this down, or speed of light over here. So everybody please write down this very important formula. So this is the important formula here, right? E naught by B naught. Now suppose in the exam if they ask you what is the ratio between E and B at a particular instant. So suppose I say electric field at a particular instant, right? Or at a particular position and an instant, right? And same way for this. So they can give it to you like this, or they can simply ask you E by B ratio. What will it be? Tell me. Hint is, look at the diagram. See, the maximums are in this ratio. Can you see that both are going again in they are dancing in the same phase, right? So if this by this, can you see when it is early also that same ratio will be maintained? So will you guys agree with me if I write over here equal to C? So they can ask you this also. Maximum of course very useful, but even for at any x comma t, the same ratio will be maintained. Now let's try this question. A plane electromagnetic wave of frequency 25 megahertz travels in free space along the x direction. At a particular point in space and time, E is equal to this. What is B at this point? And this came in JEE Mains 2019. Try this question. So clearly they have given us the electric field over here. E they have given you. E is equal to 6.3 and along the J cap, volt per meter. They want you to find the B at this point. So we can, for this we can use this formula that we just learned. E by B is equal to C, right? So we know this formula. E by B is equal to C, or I can say B is equal to E by C. Do you guys agree? Now you substitute it. So E value is 6.3 and C value is speed of light 3 times 10 to the power 8. So work out the value of B for me. 2.18 times 10 to the power minus 8, and what will be the unit? Tesla, right? This is the magnetic field strength. B is magnetic field strength. But one important thing here, they also tell us that the wave is going along the x direction. Electric field is along the J. So can you give me the direction of the magnetic field? Try it out. So what do we know? We know that the wave direction, or you can say the wave velocity, right? And here it is in space, so it will be basically C cap is E cross B. Here they have given you this is along the x direction, which means I cap. This is J cap. Cross, you have to find this. So you tell me, obviously B has to be K cap. So therefore, So the final answer for B will be this, and you put a K cap over here. So many Tesla along the K cap. Done. That's our final answer. So don't forget to give the direction. Not only you have to calculate the magnitude, direction is also very important, which we can do using this. Okay, done. Alrighty. Now, one very interesting thing, that what is the speed of the electromagnetic wave, right? We know that electromagnetic wave basically it doesn't depend on the particles. It is a vibration, right? This oscillation of the electric and magnetic fields, and electric and magnetic fields will therefore depend on the permittivity, right, of the medium, and the permeability for magnetic. This is for the electric field, this is for the magnetic field. And the speed of electromagnetic wave, right, as shown by Maxwell, the formula is very simple: 1 by root of mu naught by epsilon naught. You guys remember mu naught here is your permeability. So write down if you forgot all that. Mu naught is your permeability. Epsilon naught is your permittivity. What we had studied back in Coulomb's law. This we had studied in magnetism. And you have this beautiful formula, C equal to 1 by root of mu naught epsilon naught. So if you put the values of vacuum, so epsilon naught you know is that 8.85 times 10 to the power minus 12 I think SI units, and mu naught is how much? That 4 pi times 10 to the power minus 7 I think in SI units. So if you plug in the values, what will you get? So when you substitute these values in the formula, when you substitute it and you do C equal to 1 by root mu naught epsilon naught, you will see you will get this speed, 3 times 10 to the power 8 meter per second. You will get exactly the value of speed of light in vacuum, or approximately air and vacuum we consider the same. Okay, clear? So we get this beautiful formula, and so this is the speed of light, and so by this Maxwell's theory, he predicted the speed of light, right, in vacuum or free space, and it turned out to be this value, right? So it clearly shows light is an electromagnetic wave, a wave created by oscillating electric and magnetic fields. No medium is required, and it is traveling with the speed that exactly Maxwell predicted based on his formula. Awesome. Now if you say what about light can travel in glass or some other medium like water, right? So in other medium also we have the formula. In another medium, you will replace your mu naught with mu of the medium, and epsilon with epsilon naught with epsilon of the medium. And remember, there is this formula: if you have relative permeability, then it is mu of the medium by comparison with mu naught, and your relative permittivity is permittivity of the medium by epsilon naught. So you can always calculate it if one of these are given, or if they give you something like this. If they say it's traveling in a non-magnetic medium, non-magnetic means you will take mu naught, because it has no magnetism property, but it may have some permittivity. So if they say non-magnetic medium, then you replace mu m with mu naught. Is that clear? So again, the same formula works, and based on the values given, you can predict the speed of the electromagnetic wave. So let's try this question, which came in JEE Mains 22. So electromagnetic waves are traveling at the speed of 2 times 10 to the power 8 meter per second. Relative permeability is given to you. They are asking you to find the relative permittivity. Come on, I want all of you to try it out. Hint is, use the formulas I've just taught you. So that is why practice it, your concept will become clear. Based on what I've just taught you, can you solve this question? Come on, try. Let's see if we can make up a easier formula. Let's see if we can connect these guys. Because I wrote relative stuff here, I wrote these. So let's see if we can easily connect them. So what we can maybe do over here is, why don't we take a ratio of C by V or V by C? So let's take a ratio of V by C. Come on, let's do this, and I think it will help us in that question. You can do it without that also, but if you take this ratio of V by C, what can I write? V is 1 by root of mu m epsilon of the medium, okay, This comes in the denominator and this was in the denominator, so it will go in the numerator. So here instead of 1 we will have root of mu naught epsilon naught. Got it? Now we know that mu m by mu naught, so see we can put it all under the square root, so I can say V by C is 1 by root of mu m, I will bring the mu naught here, epsilon m, epsilon naught. Now guys take a look, mu m by mu naught is mu r, this by this is er, the relative stuff. So wow, we have got a very beautiful formula here. And if you want to move the C above over there, you can do that as well if you want. Wow! So you can get this nice formula just simply by dividing V by C. Right? Just simply by dividing, we can get this other useful formula, and I think we can directly use it. So for competitive exam and all, this formula is very useful. So let's see if we can apply it here. What did we just derive? We just derived that V is equal to C divided by mu r epsilon r. What is V? Speed of light, speed of the electromagnetic wave, not speed of light, it can be any wave. So 2 times 10 to the power 8. This one will be speed of light in vacuum is 3 times 10 to the power 8, that is fixed. Relative permeability, this is my mu, permeability mu r is given. So 1. And I need to find epsilon r. Got it? So this all will get cancelled. So basically I will get root of epsilon r is 3 by 2. So if I square both sides, will I get the answer? 9 by 4 will be the answer, and you can work it out in decimal. Done? So see, with this magic formula it became so easy. Or you could have done it from the basics also, you will get the same answer. Here's another question for you. Magnetic field in a plain electromagnetic wave is given to you as this, and see it is in Tesla. What is the wavelength and frequency of the wave, and write an expression for the electric field. Very nice, interesting question. So see, this is the question where you are getting the equation, right? And they have given us the equation for what? B, magnetic field equation. In an electromagnetic wave, this one they have given. Try out this question. So for part A, first write down the equation that they have given us. B is equal to, or first let's compare it with what we know, the standard equation. What is it? B naught sine, they have used, I told you kx can be in front, omega t, doesn't matter. So we will compare it with kx plus omega t, so many Tesla. So when you guys compare this, tell me, what is the value of k over here? So comparing, can you see? This is my k, this is my omega. So let's write that down. So k, which is basically your 2 pi by lambda, is nothing but 0.5 times 10 to the power 3, which basically means how much is that? 500. And omega is what? Omega, which is 2 pi f. So can you guys work out the wavelength for me? Absolutely. Lambda will equal to 2 pi by 500. What will be the frequency? This is 2 pi f. Again, this is assuming, and these are all in SI units, so meters and so many hertz. Did you guys get this? Yes or no? So first part is done. Second part is very interesting. Write an expression for the electric field. How do we do that? We have just been given magnetic field. Electric field expression means we are looking for something like this. E is equal to E naught sine kx plus omega t. Because remember we said it's in the same phase. Phase means this guy. What is within the bracket? You just copy it. Phase of the wave is what is within that sine or cos function. So I just copied it. So I can simply copy down the values. The only problem is the E naught, right? And they have not even given us the direction. Otherwise, direction would have been perpendicular. We would have been, we can work it out using our rule, right? Cross product rule. So basically, I have to work out E naught. How do I work out E naught? How do I work out E naught? Remember that formula? Remember that formula that I taught you? Exactly this formula. C is E naught by B naught. So write down that formula and work it out. Simple. So we'll write over here C is equal to E naught by B naught. That means your B naught is E naught by C. E naught means this is your E naught. 2 times 10 to the power minus 7. And speed of light. So you can see quite a very tiny number. This will be 2 by 3 times 10 to the power minus 15. So go ahead and copy down that value here. This will be your, we have to find E naught. Sorry, my mistake. We were given B naught, we had to find E naught. My mistake. E naught will be C times B naught. So 3 times 10 to the power 8 multiplied by B naught is 2 times 10 to the power minus 7. Okay, good. So the value looks easier now. 6 and 60. 60 volt per meter, right? Whatever its units. So here it will be, you substitute the 60 here, and here you keep the same sign. Sign kx, just copy this down. 0.5 times 10 to the power 3x plus 1.5 times 10 to the power 11t. And that is your answer done. That is your answer. We are done. Is it clear? So this is the beauty about it. This is the electric field equation. So let me write over here E. There you go, done. Now let's talk about a very interesting concept, which is energy density, right? Energy density of electromagnetic wave. See, waves always, you know what is the job of the wave, like sound wave, electromagnetic wave, they are carrying energy, right? They are basically an energy in motion. They are propagating energy. So basically we know same way, just like sound waves, these waves also carry energy as they travel. Now where is the energy coming from? Energy is coming from the oscillating electric field, which means from your capacitor. And the other energy is coming from your oscillating magnetic field, which is from your inductor. And the best part is both are contributing to equal share. It's not like C says I'm doing more work or L says I'm doing more work. Energy, this is very, very important point. Energy from electric field is equal to the energy from the magnetic field. It is divided as half-half, 50-50 split. So you can remember 50-50 split here for the electric and magnetic field. This energy equal to this energy. Is that clear? Okay, so energy is split exactly half-half. Now let's look and work out the formulas, right? So here what I meant is, suppose the energy was 10 joules, or we'll talk about the units, then it will be 5 joules from the magnetic field, 5 joules from the electric field, right? That's the idea of half-half. Now what is the formula? Let's work it out. Don't worry, these formulas are not very easy to learn, but we'll see the derivation also, that how do you work out the energy density of electric field. What is the meaning of energy density first of all? Energy density means we are trying to work out energy per unit volume, because see, the wave is propagating like this. Now what can I say? Energy of this part, the entire part. So I'll say as the wave moves, energy per unit volume. Okay, how much energy the wave is containing or traveling, right? It's in the wave per unit volume. So energy density, that's what we are going to work out, is energy per unit volume. Clear? Now, so first we'll work out the energy density of the electric field. That I told you is associated with our capacitor friend. So we'll focus on the C, this guy. And energy of the capacitor, all of you remember? What is the energy of a charged capacitor? Half CV square. Yes or no? Tell me, you guys remember that? Make me happy. So energy of the capacitor is half CV square. The electrostatic energy is stored there, which it's now going to transmit as electromagnetic energy, as the electromagnetic waves. So please write down this formula and let's work out the energy density. Now capacitance of the capacitor, so we are considering a parallel plate capacitor. So capacitance, all of you remember the formula, half capacitance will be epsilon naught A by D. A is the area of the plates, D is the distance, remember? D is the distance between the two plates, A is the area of the plates. So I'm using parallel plate capacitor formula. Now how is voltage connected to the electric field? How is voltage connected to electric field? Right? We know that electric field is V by D. So can I replace V as E times D? Yes or no? So I can replace E times D, and this is voltage square, so I have to put a square over there. Now let's simplify this, guys. So I'm getting half epsilon A D E square D square. 1D and 1D will get cancelled here. So finally we are getting. Now why have I written the area and the distance between the plates together? Because if you multiply by the area of the capacitor, the plate of the capacitor, and the distance, area times distance will give you what? That's right, the volume, right? The volume. So this part will be nothing but the volume. So we can say energy per unit volume is half epsilon naught E square. Do you guys agree with this formula? Yes or no? Tell me. Epsilon naught is your permittivity. E is the electric field strength at that particular moment. E is the electric field strength. And this is energy per unit volume. So this capital U by V I am going to denote with the energy density, which I am going to denote as U with the small e. So energy density associated with your electrostatic field or electric field is this. This is your energy density. Clear about the formula? Awesome. So now we said that these charges are in oscillation. So remember I said the electric field will keep changing because charges are oscillating, so it will increase, decrease, come to zero. So this is at any instant, right? This is happening at any instant. So now we are going to talk about the average energy density, right? Because it is changing with time, right? So we will now talk about average, right? Just like we had talked about average power, here we are talking about average energy density. In alternating current we have talked about average power, here we are talking about average energy density. So remember we have got this formula, this is for energy density, or you can say instantaneous energy density. Again we are focused on the capacitor, having area A, right, and this distance D. So how will you find its average? What will you do here? So you will say I am interested in, and this is the small u, so I am interested in average. So I will take an average of this. Do you guys agree? Let's take an average of this. Average of half is half, epsilon naught is constant, right? So these all guys will come out. And this electric field guy is the irritating guy who's varying. He's the problem, right? Now electric field, I know what will be the formula over here. We'll apply half epsilon naught, and electric field is what? E naught sine. So this will become E naught square sine square omega t minus kx, right? You can take, and we are going to take an average of that. Do you guys agree with this? Yes or no? So again the epsilon naught square is a constant, so it comes out. And average of the sine squares, we have done this in the power stuff also. If you take an average of sine square, this part, you will see it will work out to be half. See, because you can always use that trigonometric formula and you can convert it into that cos 2 theta formula, right? So you can check that and do it, but trust me, this will work out to be half. So you can try this out yourself. If you find an average of this, so you can convert sine square into cos, right, and work it out. So you will get a half over here. So this is the average energy density, right? Because since it is varying, so we like to look at average, right? We like to make things easier for ourselves, or you'll say maybe more complicated with formulas. But now if I bring this 2 down here, so basically I am getting something like half epsilon naught E square by 2. So E square by 2 I can split like this. I can write this as, E naught by root 2 whole square. Yes or no? This 2 I am writing as root 2 whole square. Guys, what is E naught by root 2? Do you guys remember what is E naught by root 2? E RMS, right? Electric field, the RMS value. So will you guys agree that the average energy density half epsilon naught, so there it was for instantaneous, it was E, here you replace it with the E RMS square. Very, very important formula for average energy density. Is the derivation clear to you? Now let's go to the magnetic field, otherwise magnetic field will feel bad, right? So we talked about the capacitor, now we'll focus on our inductor fellow, otherwise he's going to cry. Remember energy associated with the magnetic field in a solenoid, right? That inductor, that half Li square. L is your inductance, I is the current. You guys remember this formula? And if you have a solenoid like this, right, having n number of turns, carrying a current I, then you guys remember these formulas. So we had all these formulas. What was it? Half. Can you tell me the formula of inductance? And same way, what is the formula of the magnetic field? Magnetic field in a solenoid, remember, mu naught Ni. So current can be written as B by mu naught N. That all of you remember. What about L, guys? What about L? Let's say having cross section area A or pi r square, right? So I think I remember the L formula was, inductance was mu naught N square A times L. Please check. Inductance of a solenoidal shape like that. So just plug in these values, no big deal, just we'll plug in these values over here. So we'll say this is half, L we'll put this mu naught N square AL, and I square will be B by mu naught N whole square. Got it? So let's calculate over here. This one, the mu naught will be there in the denominator. So we'll get a mu naught over here. N square will cancel, B times AL. Again, AL is what? The volume over here. So we can say U is equal to half BV or BV by 2 mu naught. So U by V, I think I've got a B square here. Just check. Check, are you guys getting this? Are all my steps correct? So for the electric field we had half epsilon naught E square. Here it is half B square, but instead of epsilon naught you get a 1 by mu naught. See, same thing. So this is nothing but, therefore we can say U of the magnetic field energy density is going to be half B square by mu naught. Got it? See, we have proved the formula. This is energy density. And so similarly, just like electric field will work for the average energy density. This was the energy density at a particular instant. So this is the instantaneous of this inductor. Okay. So similarly you will get, so similarly if you work out the average, what do you guys guess? Instead of B square, I'll replace it with B RMS square. The B square will get replaced by B RMS. This is for the instant, this is for the average energy density. So we have worked out the average energy density of the electric field and the magnetic field. Let's quickly write down the formulas. So quickly write down the formulas for me. You can see they are very symmetric. Here we have E, there we have B, here epsilon naught, here 1 by mu naught. Got it? Now if I ask you, what is the relation between this? Is this bigger, or are they equal? Now to make the relation easy, rather than ERMS and BRMS, we'll write it, RMS remember is E naught by root 2. So let's replace it like that and write it. So we can say UE, the average here, is half epsilon naught. This I'll write it as E naught square, and this will become by 2. Same thing here. Okay, by 2. I've just replaced the definition of RMS is highest maximum value by root 2. So we have squared it. Got it? Now we have to check that what is the relation between these guys. Can you guys tell me? What is the relation between these two fellows? So to find the relation, let's just do a ratio, right? Let's calculate a ratio of UE by UB. So in the ratio, you can see all this half and all this business will get cancelled. or okay fine, let me write it 1/4, so you'll feel happy about it. So I'll write this and I'll write a 1/4 over here. There's a mu naught down here and a b naught square. 1/4 everybody agrees gets cancelled in the ratio. Ta-dang, ta-dang, gone, right? So what are we left with? We are left with, and this mu naught will go on top. So I think we are left with mu naught epsilon naught, and here I have left with, got it? Now when you look at E naught by B naught, remember we did that formula, it is equal to C. So this part will simply be C. This part, does everybody agree? It is going to be C square. What about mu naught epsilon naught? Remember we had this formula that C was nothing but this. Speed of light or speed of electromagnetic wave is this. C is equal to 1 by root of mu naught epsilon naught. Your speed of your electromagnetic waves, they all travel at the speed of light. Okay, and so that's basically what we have here. And so when we put that in, so when you do this, you bring it up here and square, you see you get nothing but 1 by C square, and these will cancel, and the ratio is 1. Therefore friends, that is why we said they share equal energy. The energy is split 50-50 between electric field and magnetic field, and I have proved it to you that the energy density of the electric field, average energy density, is equal to average energy density of the magnetic field. Is this crystal clear? The ratio is simply 1:1, just by simple mathematics, nothing great. So if we talk about the total energy, because half is going to electric field, half is going to magnetic field, will you guys agree that this will be the total here? This should be a plus, I think. So if you look for the total, what will you do? You will add these two. But we just said they are equal. So then I will simply multiply it by 2. So if this is my average, 1/4 epsilon naught E naught square is my average density. If I multiply by 2, I'll get the total density. See, half epsilon naught E naught square. I just doubled. This is basically 2 times. This one you can see is 2 times your average electric one. And this guy is nothing but 2 times your average magnetic one. So here I think we have a mistake. This should be 2. See, because here the pure magnetic is 1/4. This should be 2. So there is a typing mistake here, which is why I got confused earlier. This should be 2. What I am saying over here is simple, that if you want the total energy, what will you do? The average of the electric plus the magnetic. So basically your total energy, look at this way. Think it this way, very easy. The total energy, or you say the total average, is going to be U electric plus U magnetic. But these two terms are equal. So you can take either one and multiply by 2, right? So which you can say this is basically 2 times U electric or 2 times UB. That's exactly what I'm showing here, nothing great. So see, I just multiplied that original by 2 or this thing, and these are written in terms of E naught and B naught, right? And then here this is basically your total energy on the average, and same way over here. Your average of the electric will be half of this. So whatever this, 1/4 of that, right? Means half becomes 1/4 here. Same way, half of the total will be the magnetic. So basically we are saying the total gets split half into electric, half into magnetic. That's it. Nothing great, right? So basically you can just remember the total formula and then half it, right? You just remember the total formula in terms of electric magnetic, or you remember the individual and double it here, whichever one you like. Next, let's talk about a very interesting concept which is called intensity of the electromagnetic wave. How is intensity defined? Intensity basically means the energy crossing per unit area per unit time in the direction perpendicular to the direction of propagation. So imagine if our electromagnetic waves are going like this. So I want you to imagine the electromagnetic waves going like this. So you can clearly see this cylinder is perpendicular to it, right? Waves are going like this, the cylinder is perpendicular to it. Okay, let's say the area of cross section of the cylinder is A, and we are considering a time t. So by this definition, will you guys agree with me? Intensity, it says, is the energy we denote as U, per unit area, see, per unit area, per unit time. Do you guys agree? Or we can write this as AT. Simple, nothing difficult. I just took the definition and wrote it in simple formula form. I for intensity, energy per unit area per unit time. Do you guys agree? Now, let's see what we can do is, if we consider this cylindrical shape here, can you guys tell me the length of this cylinder? So when the electromagnetic wave is traveling, what will be the length of this cylinder? Tell me. Length will be what? Distance is speed multiplied by time. Electromagnetic waves have the same speed, c, right? So it will be c times t in a time t. Do you guys agree? The length of this cylinder will be c times t. Please draw this diagram and note it down. So now what I am going to do over here is, I am going to take this guy, take this intensity formula, I will multiply by L over here, the denominator, and in the numerator. Now if you guys look at this carefully, can you tell me what is U divided by AL and what is L by T? Tell me. U divided by AL is energy per unit volume. That is energy density. That is the energy density of the wave. So I can represent that with small u, energy per unit volume, and L by T is distance by time, which is nothing but the speed of the wave. So can we not say the intensity is equal to U times C? This is also a correct basic formula, and this is a nice derived formula, that it is energy density multiplied by the speed times C. Simple. Then there is formula for momentum, right? You'll say momentum, I've heard of a particle, right? But what about this? But you know that electromagnetic, there's a photon theory and all, but we'll not go into all that stuff. We'll discuss that since your electromagnetic wave is there based on de Broglie's hypothesis, we'll discuss that. You can also define the momentum, right? So suppose this wave is falling on a certain area, right, and there is a complete absorption of the energy, right? Then the momentum transferred is U by C, energy by speed of the wave, right? And if the wave is totally reflected, because you know that when something is totally reflected, what is the change of momentum? Suppose the initial momentum is P and the returning momentum is minus P. So you guys know here, if it is a reflection case, then your change in momentum becomes P minus of minus P, minus 2P. And if you take the absolute value, we take it as P, 2P, right? So see, it's basically going to be double. This is the reflection case. The momentum, change in momentum is double. Change in P is double. But you'll say, how did this formula come about? I think the proof is not given in the books, but I will prove it to you. So maybe you guys have studied, or you'll study it later, that de Broglie proposed this, that whole, the particle, the wave, that wave particle duality. And so there he talked about the wavelength associated with the particle. Remember? So according to de Broglie's wavelength, so de Broglie is pronounced as de Broglie's, right? So de Broglie wavelength, you guys remember that lambda is equal to h by p, that Planck's constant divided by the momentum. Everybody write down this equation, because I am going to try to prove this one for you. It's not given in the books, but we'll try to prove it. Lambda is h by p, write it down. So p we can say is h by lambda. Yes or no? Please write this down. And now when we talk about the energy of light, right, or the energy of the photon, so when we treat light as particles, so energy of the photon, remember energy of the photon is hf, h times its frequency, and f is what? hc by lambda. Frequency is speed divided by wavelength. So everybody is written till here, note it down. So if you look at this equation, so from here basically we've got, so let me write this on the side, E is equal to hc by lambda. So we have this. Now can you connect these guys? So we have hc by lambda and p equal to h by lambda. So if I take h by lambda, is it not p? If I take h by lambda, is it not p? So if we combine these two equations, from these two equations I think we can get E is equal to Pc or P is equal to E by C. Got it? P is equal to E by C. Everybody has got it? P is momentum, right? E is the energy of the photon divided by speed. So this, what I said, was energy for one photon. So P is equal to E by C is true for one photon. But we are talking about a wave having a huge number of photons, right? So here it will basically be, so P is equal to E by C. This is for one photon. So for the entire wave, therefore, the momentum will be the total energy density divided by C for the wave. See, I proved it for you. Clear? By the way, what is the unit of energy density? Maybe I forgot to mention that energy density is energy per unit volume. So joules per meter cube. Okay? Joules per meter cube. So that is what we are applying. And then there is one last formula which is given in some of your textbooks, the radiation pressure, right? You have seen that comets, comets, they are having this tail which is away from the sun. Always the tail points away from the sun. Why is that? Because the sun is emitting electromagnetic radiation, and because of this radiation pressure, it is pressing the tail away, and that is the formula you are going to study, is intensity by C. So please write this down. Radiation pressure is intensity by C. So this PR, what I have written over here, this is your radiation pressure, and you can remember it by the example I told you, that here is your sun which is emitting electromagnetic waves, and this is why your comet, the tail of the comet, it points away from the sun, because it is of the radiation pressure, which is intensity by C. So all these important formulas, good to note it down and learn them, because if they ask you questions or multiple choice questions, you can easily solve it. Now let's take a look at some questions. So what is the question here? Light has an energy flux of 18 watts per centimeter square. Okay. Now don't get scared when you see this watts. Watts is basically what? If you're looking at intensity, see energy per time. So which reminds us, let's talk about the units of intensity. So intensity is this. What will its units be? See, because you can see energy, so one simple unit will be what? Joules per meter square per second. But you know joules per second is what? Watts. So we can also write this as watt per meter square. Joule per second is watt divided by meter square. Clear? So that unit of intensity will be very easy from the formula. So here I think they have given you energy flux, means they have given you intensity, watts per centimeter square, right? Is falling on a non-reflecting surface at normal incidence. If the surface has so much area, find the average force exerted on the surface, wow, during a 30-minute time span. Very interesting question from NCERT. So since this is falling on the non-reflecting surface at normal incidence, and find this when it is put on this time span, right? So basically you can see that light is falling on the non-reflecting surface. So something, you have a situation like this, where let's say you have a non-reflecting surface over here, and your light, which is an electromagnetic wave, is falling on it. Now they are asking us for force exerted. Force by the wave. Force means, force is created by rate of change of momentum, right? Force we know is nothing but change of momentum, delta P by delta T. That means I have to go to my basic momentum formula which I taught you, right? That means we have to go to this momentum formula. And for completely reflective, we use 2u by c, otherwise we use u by c. So we have to use the momentum formula. So clearly I have to work out the change in momentum or momentum, which is u by c. But I have been given intensity, I is given to me 18 watts per centimeter square. From there, how do I get the u? We know that intensity is u by area and time. So will you guys agree with me that U is IAT? That's it. So can you guys calculate it for me? I think we can do it easily. Can we do it? The intensity is given 18 watt per centimeter square. So 18 watt per centimeter square. Area is given to me as 20 centimeter square. And time is 30 minutes. So I might want to convert that to seconds. So 30 minutes multiplied by 60 seconds. This centimeter square will get cancelled. So see, we have worked out the energy density over here and we have to divide that by C. Got it? So you calculate this. This is your U. From there you calculate your delta P. Or maybe we can keep the time T because anyway we have to divide it, right? So maybe we can keep this as T. So this is working out to be, delta P is working out, or U is working out to be 18 times 20 T. So delta P, which is U by C, correct? And then I think the force, you just divide this by the time, the delta T. Check. Are you guys getting it? Okay. So here see, if you work out, force will be delta P by T. This was actually, I'll put it as delta T if I use the delta notation. So delta P by delta T, which is nothing but 18 times 20. So work this out. See here, you'll get 6. So that is the answer. Done. Such a beautiful, nice question, right? This is how you work it out. So because we got force, see, we worked it backwards. Force, rate of change of momentum. That means I need momentum formula. That means I need energy density. From energy density, I get from the intensity. You work it out, delta T cancels, you can easily solve it. And if they had given you a perfect reflector, means all the light is reflected back, then the change in momentum is doubled. So force answer will be exactly double of this. Exactly double of this. Got it? Next question. Calculate the electric and magnetic fields produced by the radiation coming from a 100 watt bulb at a distance of 3 meters and assume the efficiency of the bulb is 2.5% and it is a point source, right? So basically you have a tiny bulb, or you have a bulb here which you are considering as a point source. It is 100 watts, okay? And you want to find the electric field and magnetic field produced at a distance of 3 meter. So we are considering some distance here, let's say 3 meter, and efficiency is 2.5%. So what will be the electric and magnetic fields produced here? Try this, nice question. See, why did I consider this sphere? Because the light is being radiated all around, right? So it is not only coming here, it is going everywhere. Do you guys agree? So, and again, see, we have to work with the concept of how much intensity each part is getting, because energy per unit area divided by the area. Now here, what is the area we are talking about? The surface area of a sphere. What is the formula for that? Tell me, guys. What is the formula for surface area? 4 pi r square. Very good. So here 3 meters. So it's basically going to be 4 times 3 times 3. So there we have a, this is the area we are talking about, correct? And now 100 watt bulb, 2.5% efficiency. That means most of it is being wasted, right? Only 2.5% is being converted to electromagnetic waves, right? So we can say that the intensity, which is basically your energy per unit area per unit time. Now U by T, energy per time, is nothing but power. They have given us 100 watt bulbs. So do you guys agree that this is nothing but power by area? Yes or no? Energy per unit time is power. So power by area, see, they have given us 100 watt bulbs. How much intensity are we getting from it? 2.5% of 100 watt divided by this area, 36 pi. Do you guys agree with this logic? 2.5% of the 100 watts, right? This is the 100 watts and so many meters square. So I have worked out the intensity. Yes or no? Tell me. So if we simplify, we are basically getting the intensity is 2.5 divided by 36 pi. And what will be the unit? Watt per meter square. But they've asked us to find the electric and magnetic fields. How do we do that? Tell me. Intensity we said is U by AT, and it is also U energy density times C, right? So see, a lot of connections we have to make over here. So intensity we have got, and intensity formula we know is energy density of the wave times C. Now what is this energy density formula? U, so we have to connect a lot of formulas here, it's all a game of formulas. U, if you remember, was this, the U average was half E naught, remember this formula, half epsilon naught E naught square. So from there we can work out the value of epsilon naught. So that's it, what you have to do, that this will be your intensity of the entire wave will be half epsilon naught E naught square, correct? So from here we can work out U. U will be I divided by C, and which is half epsilon naught E naught square. So from here you can easily work out the maximum, so electric field, so you can work out the epsilon naught, from there you can get the RMS if you want, right? So you work out the epsilon naught and E RMS will be epsilon naught by root 2. Same way you can work out the B naught, right? Or B naught you can get by E naught by directly from here. So you get your B naught and then your B RMS will be. So now it's just a game of calculations, right? It's just a game of calculation because I got you till intensity, you divide that by C, and now you just substitute these values, you get your epsilon naught. So yes, there is some lengthy calculations here, but we can easily work out the magnitude or the RMS value of the electric field and the magnetic fields at any point. We can easily predict it from this. Isn't this a beautiful question? Okay, so we started again, take a look, what did we do? We started with intensity because we had to take at a specific distance and the wave is spreading all around. It is going here, it is going here, it is going everywhere, right? The wave is going everywhere. So I have to take concept of intensity per unit area, per unit area. So I did that, got the value, then I used this important formula, U times C, and then I worked out, because U I know I can associate it with energy density, I know I can associate it with electric field maximum value or RMS value, whichever formula you use the correct formula and substitute that. And now I'll leave you with an interesting homework question which I want you guys to try. So here's your homework question. What is the question? We have a laser beam of intensity given to you this much. Remember we talked about intensity, energy per unit area per unit time, which is basically power per unit area, right? Watt per meter square. Find the amplitudes of the electric and magnetic fields in the beam. Amplitude means your maximum values, right? Your maximum values of electric and magnetic fields. So very nice, interesting homework question. All of you please try it out. It's a very simple question. I'm sure you can do it. So go ahead and try out this question and do let me know your answers by putting it in the comments below. I look forward to reading your answers and I promise to reply to them. So guys, go ahead and try out this homework question. Hope you guys enjoyed this class on electromagnetic waves, and do check out the courses on our website manochaacademy.com and our Android app Manocha Academy. All the links are given below. As you know, we have courses on science, maths, coding, AI and our IIT NEET Foundation courses. In our courses, you're going to get live classes, concept videos, quizzes, questions, mock test and revision notes. So guys, do check it out. Make sure you subscribe to our YouTube channel, follow us on Facebook, Insta and X. So stay connected with Manocha Academy and just keep on learning.